So hello everyone, this is lecture 4 for the quantum mechanics. In the last lecture we have discussed about the wind displacement law and the basics about the black body radiation and how they are produced and how we measure and how we get the graph, this kind of graph for the black body radiation and the spectrum. So we discussed all the topics and the Stephen's law. Today we will study that there were scientists and theoretical physicists who tried to get this graph by theoretically. Means now we have graph, now we want to find an expression or mathematical expression which gives us the same graph as we are getting from the experimental methods. Okay, so first it was our Rayleigh, and first we will study about that because he studied all the graph by the classical method. Means we take all the things according to the classical physics and then we try to find this. So let's see what they did. So first of all we have this graph, and in this axis we have intensity, in this axis we have lambda. So and intensity is nothing but is proportional to energy density, because there was at that time intensity is directly proportional to the amount of energy falling. Okay, so it's a forget about anything about the photoelectric effect and the quantum energy and all, because we didn't get there yet. We are in the very starting with the classical physics. We know that it's the amount of energy falling, okay, on the surface, that is intensity. Okay, so intensity is directly proportional to the energy density. So intensity and energy density is what? Energy density is energy per unit volume falling. Okay, so we will take this u lambda as energy per unit volume per unit wavelength. So units will be joule meter to the power -4. So meter -3 because of volume and meter -1 because of lambda. Same if you plot the frequency graph, then it will be shifted to this side because lambda is decreasing and frequency will increasing, so you will get this kind of curve. So for that u nu will be J joule per unit meter cube hertz. Okay, so this will be your energy density which you will plot in this side. So you will get the same curve. Now let's see some definitions. So u lambda is nothing but energy per unit volume per unit wavelength, and u nu is nothing but energy per unit volume per unit frequency. And if you want to find the energy per unit volume itself, so you will just multiply with d lambda, and here you will multiply with d nu, that is frequency. So you will get the energy per unit volume. Okay, so or you can see that u lambda d lambda will be energy per unit volume, and divided by d lambda will give you per unit wavelength. So it is this and this is. So these are just the expressions you need to remember, and how we are getting these expressions, that is the point here. Now we will come to the thing which we will discuss today, that is Rayleigh-Jean's law. So this is our curve. Here we plotted u nu, that is frequency. Here it is frequency. So frequency curve will be like this, because with increasing temperature, frequency, this curve will shift toward the right side, and the wavelength curve shift toward the left side. So here is it is u nu in the y-axis, and here it is mu. So this is classical radiation theory, that is Rayleigh-Jeans. Both have explained. Okay, using the classical law we will find this curve and find the energy, and let's see what we will find. So let's try to find. So what is the objective here? To find theoretical expression that reproduce the experimental graph of the black body radiation spectrum, that is the expression of energy density emitted in the range lambda plus d lambda, or in frequency range nu and nu plus d nu. So it is our objective is to find a theoretical expression which will reproduce this experimental graph of black body radiation. Okay, between any mu plus d nu frequency, that graph should be matched with it. Whatever we are getting here, the expression, the mathematical expression should give us the same. Now u nu d nu is energy per unit volume, okay, in the frequency range mu plus d nu. Okay, so if this is our lambda wavelength curve, then between this, the energy per unit volume will be u lambda d lambda, energy per unit volume in the wavelength range lambda plus d lambda. So let's see, these are the expressions we described mathematically. Now what Rayleigh-Jeans do? So he assumed, so first of all there is any body. It was in the 1900 they did this. So we have any body which is heating, and it will gonna emit radiation. So between lambda and d lambda there will be some radiation emitted. So there will be this energy per unit volume per unit lambda, and d lambda will give you total energy per unit volume between this range. So we'll study that. Okay, only that energy. So between this range, it will gonna emit all the frequencies, all the wavelengths between this range, all lambda you will get. Okay, then you will plot them. So theoretically, he assumed, or they assumed, there is this cube, hollow cube, with length a. Okay, now this wall of this cube is heated, and if it is heated, then it will gonna produce EM radiations, and they will hit to the second wall and they will be absorbed. So we will observe them. Now see, first question was that why heating of this wall is producing EM waves. So answer to this is very simple. This wall contains atoms, and atoms after heating they will try to oscillate, and they will oscillate, definitely they will oscillate, and oscillation of atoms are like a oscillation of charge. And we know from the Maxwell's or the electromagnetic theory that with oscillations of charge there is a production of electric field, and change in electric field produce magnetic field. So that's how this is oscillation of atoms produce the EM radiation. Okay, and now if you are just considering the atom oscillation, then from the lattice vibrations we study in the solid state physics, this maximum wavelength produced by this atom is limited. Okay, and that will be, if this is any crystal and we have crystal parameter a, then minimum lambda will be 2a. Okay, minimum lambda will be 2a, the possible wavelength for this radiation will be 2a. And let's say if it is copper crystal, and for that a is nothing but 3.6 into 10 to the minus 10, then you will get lambda will be this, means minimum lambda will be this, it can't be less than this. And if you want to find the max, because it is minimum lambda, so it will have maximum frequency sum. So now frequency will be v upon lambda, this is the speed of sound in the copper, so it will be 2500, and lambda is here minimum. So maximum frequency will be this, means this copper crystal can't produce frequency greater than this value, 3 into 10 to the power 12 hertz. This will be the maximum frequency produced by this crystal. Now see, this is very less than the visible region frequency, that is this. So a normal object like this can't produce ever the visible light. Okay, if there is oscillation of atoms only. Okay, so that was the reason, and we studied why we are getting the EM radiation, because of the charge oscillation. Now see, we know some objects that they will glow after heating. Okay, and glowing is only possible in the visible region. So how we are getting this visible region or the visible radiations? So now in the atoms we have electrons. So this limitation in frequency is only because of the size of the atom and the mass of the atom, because with higher mass they can't oscillate with that higher frequency, but the electrons inside these atoms can oscillate, okay, with the higher frequencies. So that's how we get the radiations, higher radiations, means in the higher range with higher frequency. So with atom oscillation you will get this is your maximum frequency, but with the electron oscillations you will get higher frequencies also, means UV, visible and infrared radiations, all you will get. So that's how he explained the radiation term. Now you get the thing that how we are getting all the radiations, and who are producing these, and what are the reasons behind these radiations production. Now see, if there is waves, okay, we are having waves, so they will just say this is our first wall, this is our second wall. So radiations are emitted from here, and they will be absorbed and reflected from the other wall. Now see, if two waves are like this in this way, then we will have the standing waves, means definitely there are like two walls and we have a rope, so we'll get a standing waves. Now standing waves can have multiple modes of vibrations, okay, or the modes of oscillations, we call them states. So you can check my lectures on solid state to get the much information about the density of states and the lattice vibration and the modes of vibrations, so you will understand this more then. So it can have all the possible states of vibrations. So with the standing waves you can have this kind of oscillation, this single wave, means here lambda will be 2L, because length will go like this, and this length is L, then lambda will be 2L. You can get this state also, or this mode of vibration where length is equal to lambda will be 2L by 2, and you can get this kind of also, lambda equal to 2L by 3, and with increasing modes you will have this kind of, and it will go to infinity, 2L by n. So lambda will be 2L by n. So there are infinite possible states of vibrations. Okay, so these when they come back and form the standing waves, so they will have infinite number of modes of vibrations possible. Okay, now see, if you need to find the energy, means this energy per unit volume, so you need the number of energy states or the oscillation states between this frequency nu and nu plus d nu. You need to know the amount of energy between this region, only then you can find the energy per unit volume. So for that you need to find the total number of modes between these frequencies and just multiply with the energy and you will get the answer. So how to find the number of modes between nu and nu plus d nu? There is a formula from the density of states. I will show you. Just wait for a second. First, let's see if this is our mode of vibration. Now consider it like this spring system. So there is a spring system and we stretch this mass and release that. Okay, so it will gonna have some energy that will be k. If amplitude is a1, then k by a1 is square divided by 2. This will be energy. Okay, and if you not a1, if you stretch it up to a2, then you will get k a2, some other energy. Okay, k with a3 you will have some other energy k a3. Okay, but see, frequency of this kind of oscillator is omega equal to under root k by m, where k is our spring constant, and this is independent of the amplitude. So you will have the same frequency but different energies. Okay, so what this shows? This shows that this single mode with same frequency or same lambda, you can have all the possible energies possible here. Means all the states of energy, all energies are possible here. Okay, so it can oscillate with E1 energy, with E2 energy. Okay, so it can oscillate with any amount of energy. So how it is possible? Means if we get this thing that how many states are there, then how we gonna find the energy? Okay, because if it is gonna oscillate with all possible energies, it will also oscillate with all possible energies. Same for this, same for this. So we need to find an average energy for a single mode, and it will be applicable to all states. Means all states will have that same average energy. Okay, so we will see how will we find this. First we need to find the number of modes between nu and nu plus d nu. So how you can find this? So this is our energy per unit volume. So this will be equal to number of modes multiply energy of every mode. So this will be a total energy. This is number of modes per unit volume, and energy of one mode. This will give you total energy per unit volume. So to find this is your number of modes per unit volume, number of modes in the frequency range nu plus d nu per unit volume, and this is your average energy of one mode. So g nu d nu for the EM waves, this is the value for g nu d nu, number of modes per unit volume. So this is came from the density of states. You need to see those lectures first, only you will understand. But here you just need to remember this number, that number of states per unit volume will be came out to be this 8 pi over cq mu square d nu. Okay, so this will be the value, number of states per unit volume, means between this range mu and mu plus d nu, you have that number of modes per unit volume. Now if this is the g nu d nu, then u nu d nu will be this value multiply average energy. So this will give you the total energy per unit volume between this range nu plus d nu. Now u nu is d nu divided by d nu. So you will get this term 8 pi mu square divided by cq and e. So now this is your expression you have for u nu, expression for u nu and mu, but you can't plot this. Means you need this thing u nu and nu to plot this, and you have this, but still this is a variable, the average energy, because you didn't find this value yet. So how can we calculate this average energy? So this is the game of this average energy, all the game is of this. So let's see, to find this average energy, what Rayleigh Jeans do. So they followed all the rules of classical physics. Okay, means if this is your first ball, this is your second ball, then all possible frequencies will be produced by this ball, and all possible energies will be produced with the oscillation, because this is continuous, and all possible energies will be absorbed by the second ball because this is continuous. So these are the assumptions. Atoms, electrons in solid can produce radiations of frequency mu with all possible and continuous energies. Atoms or electrons are considered like a classical oscillators. Okay, in the first ball, a atom or electron can absorb all sorts of energy from EM radiations present inside. So these are the true assumptions of classical theory. Any amount of energy can be exchanged between wall and the EM radiations. So see, any amount of energy will be produced by this, okay, any amount of energy will be absorbed by this, and radiation and between this wall, the exchange of energy will be all possible. I mean, continuous exchange will be there. Okay, so these are the assumptions. Now based on this, we will see how to find the average energy. So we will use the Maxwell-Boltzmann distribution law. So let's say we take an example. We throw 100 balls, small balls, inside a box. Now they all will have different energies, means different amplitude after falling inside, because they will maybe some will fall like this tilted angle, some will fall like this, some will fall like this. So all will have different amplitude inside that box. So all will have different energies. So some will have maximum energy, some have minimum energy. So that is the case here, that these are the particles, and they will have, some will have maximum energy, some will have minimum energy, some will have middle energy, and all possible energies we have for the particles. So there will be a range of energies for these particles. So that's how we can find the average energy. So let's see, this is the range. There will be maximum energy and there will be minimum energy. There will be some energy in the middle half or somewhere else. So if this kind of distribution we have, this is Maxwell-Boltzmann distribution, then to find the probability of energy of any E, means at the value of energy PE will be equal to, means the probability of finding any one energy will be this, means number of particles with energy E, the probability of finding this will be this, exponential minus E by kT divided by kT. So this will be the probability to finding the particles with energy E. Okay, so modes, so we have different, all the modes, so it will be this for particular energy E, this will be your possible mode. Now see how can we find the average with the help of probability. So see, it's like you need to find the average marks inside a class, and you know that n1 students got means 3 students got n1 marks, 4 students got n2 marks, and 5 students got n3 marks. So let me show you this thing. Now 3 students got n1 marks, so 3 n1, 4 n2, 5 n3 will be total marks, and divided by 3 plus 4 plus 5 will be total students. So this will give you the average marks inside a class. This is the n1 marks obtained by 3 students, n2 marks obtained by 4 students, and 3 marks obtained by 5 students. So this will be your average marks. Now see, just divide this 3 divided by this whole term, 4 divided by whole this term, 5 divided by all this term. So we can make this like this. Now this is the n1 marks obtained by 3 students. So this is the probability of obtaining n1 marks, because 3 students obtain that marks and total number of students will be this. Number of students obtained n2 marks will be 4 divided by total student. Obtained marks n3 will be 5 divided by total student. So this is nothing but probability of obtaining n1 marks, probability of obtaining n2 marks, probability of obtaining n3 marks. So average of n is nothing but n1, pn1, n2, pn2, n3, pn3. So that's how you can find the average. And this is your summation npn. If there are one more, then it will be n4. Okay, it will go like this. Now this is a discrete thing, but in the energy which we are discussing, so here we have continuous thing, means there will be continuous energies between E minimum and E maximum. So average energy will be, the summation will be substituted with integration. Okay, so for continuous summation we use integration. So this is energy and probability of energy, so this will give you your average energy. So this is your integration, and this is just a normalizing term, because PEDE will give you 1. Okay, so that's how you just normalizing this thing to get the average energy. So this will be your average energy. Now we will use this PE because of Maxwell-Boltzmann distribution. This is, so this will be your term. So you will just substitute here in place of PE exponential minus E by kT and exponential minus E by kT dE. Now after solving this, just use the by part integration here, and it will be like taking first as, this is first function, this is second function. So E integration of this minus differentiation of this, integration of this, and this is the integration of this will be exponential minus E by kT divided by minus 1 upon kT. So after solving this, you will get average energy will be kT, and this is the equipartition theorem. So try to solve this. It will be like this. That's how you can find this. This will be your numerator term, this will be your denominator term. Then you will put the limits 0 to infinity. With infinity, exponential minus infinity will give you 1 upon infinity will give you 0 here, this will give you 0 here, this will give you 0 here. So 0 minus, now you will put second limit, that is 0. So this will give you 0 here, kt square here, and kt here. So this will give you minus kt. So it will be minus kt here. So it will be minus plus, you will get kt here as your average energy. So that's how you get the average energy, that is kt. Now you will just substitute in the place of average energy, that is kt. So you will get the whole expression. So it will be u nu will be 8 pi mu square divided by cq into kt. Now u nu d nu will be your average energy per unit volume per unit wavelength will be this. Sorry, frequency will be this. Now if you try to plot this, it is going with the square of frequency, and all things are constant because temperature is constant, things are constant. So u nu will go using this expression, this will go like this. So this curve was very helpful because this explained for the lower frequencies, this curve explained the graph very well. This was your experimental graph and this was your Rayleigh's graph. So this explained this graph very well. But what we see here, that according to the Rayleigh's prediction, at the ultraviolet range, it will curve will go to infinity, means the object will absorb or emit the infinite amount of energy. Okay, so that's how we are saying that it will emit at the infinite amount of energy at the UV frequency range. Okay, so this was called the UV catastrophe. That's why we called it, because at UV we are getting infinite amount of energy according to the Rayleigh's law. But this is not the real condition. We will get this kind of curve experimentally. So that's where Rayleigh's fails. But he was true for the means he succeeded for the small frequency ranges or higher wavelengths, but for lower wavelength he failed, and for higher frequency they failed. Okay, now why they failed? See, this was your mathematical expression, because we are getting this because of mu square, and there is nothing wrong in this because this is a simple mathematics term for the number of modes, and this will remain same, and this is independent of frequency. So we are getting this because of this, and so there will be something wrong in this. Only then we will get this, because this will remain same and this will remain same, then we are bounded to get this result. Okay, and then there will be something wrong with this. But we considered this average energy also with the all possible things, means this is classically true, and if it is true, then and what we considered here, these assumptions. So with these assumptions we are bounded to get this result only, and this. But this is not the real condition, means experimentally we are getting something else. So where we are wrong? Okay, so we are wrong here because of we consider the continuous energy absorption and the emission. Okay, it is not right like this. So then the person came was Planck's, and he thinks out of box, and he says that the emission and the absorption of radiation will be discrete, means it can't be continuous, it won't be continuous. Only then he can explain this, means he was not himself satisfied with this thing that it will be continuous, means it won't be continuous. But he said that I am able to solve this curve only with the discrete amount of energy. So see, means this is fixed value and this is kt value, so there will be something wrong with this only. So we will go into more detail in the next lecture with this, means what was the Planck's theory. So in today's lecture we just entered the Rayleigh's, and just go through this lecture again so you will understand more. So, okay, till then, thank you everyone. I'll meet you in the next lecture.